Okay, so now we're going to do some examples of work problems in the calculus setting, and we're going to start with a spring problem because it's going to identify some of the central issues that come up. So the example that we're going to start with, my example 1, is example 3 from the textbook, and there's some issues with the way this problem is written that will apply to a lot of physics-type problems in this setting. The first thing is, you need to watch out for the fact that when we're talking about work, we're talking about displacement. So if the way the problem is written is not in terms of displacement, you need to make it in terms of displacement. That's number 1. Number 2 is you have to have consistent units. In the standard system, that's going to be joules, newtons, kilograms, meters, and seconds. And if you don't have those units when you're doing the computations, you need to put them into those units. So in this problem, you'll notice that the way the problem is asked, it involves centimeters. And not only does it involve centimeters, but it involves position instead of displacement. And so we're going to have to address both of these points. So what does the problem say? It says you start with a spring whose natural length is 10. So we're going to think of that as x is equal to 0. Then we take the spring and we stretch it from 10 centimeters to 15 centimeters. That is, we have a displacement of 5 centimeters. And then it tells us the force that it took to do that. Of course, I'm not going to be able to use these numbers in combination with each other because the force unit is newtons and the distance unit is centimeters. So the centimeters are going to have to be converted into meters in order for this to make any sense. So what I'm going to do is I'm going to rewrite the problem in terms of displacement and meters. So the original setup for the problem looks like this. X is equal to 0, which really corresponds to a natural length of 10 centimeters, but we're going to call it 0 meters. To take the spring and stretch it from 10 centimeters to 15 centimeters, that is, from its equilibrium position, or its natural length, 5 centimeters further, took 40 newtons. So to move that spring from its equilibrium length to a length of 15 means that we've displaced this 5 centimeters. But I don't want to work in centimeters, I want to work in meters, which means my displacement here was 0.05. Okay? It took 40 newtons to make that stretch. So the force required to hold the spring at the position 0.05, to hold it there, that force is equal to 40 newtons. And that's the force that is induced by the spring at a displacement of 0.05 meters. On the other hand, Hooke's law tells us that that's equal to the spring constant times that 0.05 meters. And that means that the spring constant must be equal to 800. Okay? Because this is an algebraic equation that I can simplify. I can take 40 is equal to k times 0.05, divide both sides by 0.05, and you'll get k is equal to 800. So the first part of the problem, this part of the problem, was asking us, or giving us enough information to find the spring constant k. So this is all about finding k. The second half of the problem is the calculus half. So that's this stuff. How much work is done stretching it from 15 centimeters to 18 centimeters. What that's asking is, if I'm already at an extension of 5 centimeters past its natural length, and I go 3 more, so I take the spring and I stretch it even more to 8 centimeters past its natural length, how much work did it take to get that thing from here to here? The first thing it gave me was a force, which is just the force that it takes to hold the spring steady here. The second thing that I'm being asked is, okay, now actually how much energy got used? Knowing what I know about the spring, how much energy got used taking the spring from this position to this one? How much work was done? Okay, so now we can use the work equation. I know that my F, where x, remember, x here is displacement, that f of x is equal to 800x. And I want to know the work used to stretch from 5 centimeters of displacement to 8 centimeters of displacement. Remember, the 15 and the 18 are relative to the natural length of the spring, which is 10. And I don't need that. I just need to know how far the end of the spring went. And that means I can recast this problem entirely in terms of displacement. So what that means is that I could write the work is equal to the integral from 0.05 to 0.08 of 800x dx. Using the power law, that tells you that we're looking at 400x squared evaluated from 0.05 to 0.08. Plugging the numbers into the fundamental theorem of calculus gets us 400 times 0.08 squared minus 400 times 0.05 squared. And when the dust clears, you get 1.56. Since you've set all of this up in standard units, then the output is in terms of joules. Okay? So when you're doing this problem, the important thing was, 1, knowing what the work equation is, but 2, recognizing that the difficulty in the problem is making sure that it's consistent, that when all the units are lined up correctly, that you have a force expression that's consistent that you can put into the work equation. Okay, so the last example that I want to talk about is the sort of problems, a particular type of problem that's sort of notorious in calculus classes, which are tanks filled with water. And if you've seen these things or will see these things in engineering context, those classes love tanks filled with water. Physics problems love tanks filled with water. Sometimes the tanks are static, sometimes water is flowing from one tank to another. So at least for us, this is our introduction to a tank full of water. Okay, so here's what the question says. We have a conical tank of water. So this is example 2. We have a conical tank of water that looks like this. The height of this tank is 10 meters. Okay? And the water is 2 meters below the surface. That is, the water is at a height of 8 meters. So this is the water, and the height of the water is 8 meters. The radius of the tank is 4 meters. And the question is, with all that information, how much work does it take to get all the water out of the tank? And so the way that physics thinks about this and calculus thinks about this is sort of absurd, but the most intuitive way to think about it is you slice the water into slabs, you figure out how much water is in each slab, and then you figure out how high you have to lift that particular slab of water to get it out of the tank. So this is why this is in the volume section, actually, because the idea of taking the water and chopping it up into slices corresponds exactly to when we were measuring the volumes of surfaces of revolution. So how are we going to do this? We're going to think about taking a slab of water. So let's just cut some little circle of water out here. So we take that water, which is somehow solid, maybe it's ice, and we slice out a slab of it. The first question I've got is, well, where is it located? Right? I have to have some sort of coordinate system here in order to make this work. You can do this either way, but frequently in this class, it's going to be convenient to let 0 be equal to the height of the top of the tank. And then if we orient this in a downward direction, then gravity will be a positive force. So this is the positive direction, which is why I've drawn that arrow down. Okay, so x is downward oriented, 0 is at the surface, and we're going to take this slab of water and we're going to lift it up out of the water. Well, where is that slab located? It's located at position x. So we think of the location of that particular slab as being at height x. So how far is that slab from the top of the tank? Well, it's x. So this slab is located x units from the top of the tank. Okay, because the distance here is x. If it's located at position x, and this was 0, and this is x, then this distance is x. So the height that I have to lift that slab of water is x. That's actually why you orient it this way. What is the volume of that shape? Because what I'm really after here is a force. And force is a weight. And weight is equal to something like mass times gravity, right? And I need to know the mass of the disk, but I don't know the mass. I could figure out the volume, and then once I had the volume, I could multiply that volume by the density of water to get the mass. So here's the whole chain of things that you need to do in order to figure out how much work it takes to get that slab out of the tank. If you knew the volume of the slab, and here this is what I'm thinking of as the slab, then you could take that volume and you could multiply it by the density of water. When you do that, the thing that comes out is a mass. So this would be a mass, right? That's a mass. The volume of the slab times the density of the water is equal to the mass of the water in that slab. Then if you multiplied that by the force of gravity, you would get a force, right? So that's the weight of the slab, is that force. So this is a weight. If I want to turn that into work, I have to figure out how much or how far I had to take that weight and move it. Well, that's equal to a height. So if I took that force and I multiplied it by the height that I had to lift it, which is x, remember, because that's how far I've got to move this, then you get F times x, which is equal to work. So that's sort of the chain of reasoning that we're going to use here. We're going to start with the volume. We're going to multiply by the density of water, and that's going to give us a mass. Then we'll multiply by gravity, and that will give us a force or a weight. And then we'll multiply that by x, which is the lift, and that will give us a work. And then we'll just integrate over the expression that we get from all of the places where these slabs are located, which will be from 10, because remember, this tank is 10 tall, so the first slab is located at x equals 10, and the last slab is located at x is equal to 2. So step 1. Find the volume of the slab at height x. So let me draw the setup here on the side. Here's the water. I know that this is supposed to be x is equal to 0, and then we go down until we get right here, which is x is equal to 10. I'm picking out an arbitrary slab right here in the middle. I'm saying its position is located at x. So I know that this thing is delta x tall. Can I figure out the area of the circle that it sweeps out? Okay. So the shape that I'm going to use to figure out the volume of the slab as a function of where that slab is located is going to be based on a triangle that looks like this. I know this is 4, and I know that this is 10. And if this height right here, if this position is equal to, if this is at x, then this length right here is 10 minus x. And what I really want to know is this length, because that's the radius of this thing, right? So the radius of the circle would tell me its area, and then I could use that to find the volume. So this setup right here, I should point out, if this is 0, then this is x, then this length is x, and this length is 10 minus x, because x and 10 minus x together make the whole length, which is 10. So what the rule of similar triangles says is that you can set up proportions of triangles, and proportions of similar sides between two triangles are equal to each other. So I've got 3 pieces of information. I've got the 4, I've got the 10, I've got the 10 minus x, and the unknown that I'm after here is the radius r. And so the proportion that I can set up is r over 10 minus x, that is the short leg of the triangle divided by the long leg, is equal to the short leg of the big triangle divided by the long leg. And that will give me an expression for the radius of this circle right here. Remember, this is a circle in 3 dimensions. This, if I solve it, is going to give me an expression for r in terms of x. And that's really what I need, because the radius changes as I move up and down the cone. So you get what r is equal to 2/5 10 minus x which is equal to 4 minus 2/5 x. Okay, so it actually, because we're going to be squaring this, that actually is probably easier to leave the 2/5 outside. So we can just imagine here that instead of writing it like this, I'm going to leave it like this. So now what have I been working on? Well, I'm trying to figure out what the volume of this little slab, so that slab is that slab right there, what the volume of that slab is a function of how high up I took the slab from. And the expression that I'm going to get out here is that the volume of this thing is equal to pi times the radius squared times the height, which is delta x. That's just the cylinder formula. So this expression right here is the volume of this cylindrical slab. Okay? So what's the mass of that slab? Because after all, the mass is what I'm going to have to move. So the mass of the slab, step 2, is equal to density times volume. And the density of water is 1,000 kilograms per cubic meter. So 1,000 kilograms per cubic meter times pi r squared. This is a mass. This is measured in kilograms. Okay. Now if I want the force that it takes, I'm sorry, now if I want to make this into a force, well, this is a mass. If I want to make it into a weight, that is a force, I have to multiply that by the force of gravity. So if I want step 3, I want this to be a weight, which is the same as a force, then I need to take that expression, so 1,000 pi 2/5 10 minus x squared, and I need to multiply all that by gravity, which is 9.8 meters per second squared. If I want all of that to be a work, I have to take all of that and multiply it by how far I need to lift it. So step 4 is a work expression. There's a delta x in here, because this is supposed to be a volume. So the work expression is going to be work is equal to the weight, so 1,000 pi 2/5 10 minus x squared delta x, and then I guess there's, if we multiply by 9.8, we get about 980 right here. And all of that has to be multiplied by x, because x was the height that I'm taking this slab and lifting it. So all of this work, the mass of the slab required that I calculate the volume of the slab. Once I know the volume of the slab, I have to multiply by density to get the mass of the slab. Once I've got the mass of the slab, I have to multiply by gravity to get the weight of the slab. Once I have the weight of the slab, I've got to figure out, okay, well, how hard is it to lift this from a position x to the top of the tank, which is position 0. That's why we multiply the displacement x. And I have to do that for every slab inside that cone. So what we're going to do is we're just going to take this. So this work expression right here is the work done to take an arbitrary slice of that cone, an arbitrary slice of that water, and push it up to the top. So we're going to integrate from 2 to 10 because that's the location that the slices are on. Remember that we're going to integrate in the order of the positive orientation here. So we'll start cutting at 2, which is where the first slab is, and then we'll lift that out, and then we'll take the next one and lift that out, and we'll take the next one and lift that out, and so on and so forth. And so the work done is going to be equal to the sum of the little works, right? This is the work delta W is equal to the work for each slab. But I have an expression for that, which was 980 pi times 2/5 10 minus x squared times x delta x. And if I want to make that into not just an approximation, but an actual real value, work is going to be equal to the integral from 2 to 10, because that's where the slices are located, 980 pi x 2/5 10 minus x squared dx. And so this thing right here, that's the work integral. Okay, So now why did they teach you U substitution? Because when you multiply this out, you have an x inside of this square right here, and then you've got an x on the outside. So you can either multiply this. There's two different ways to go. You can do this with the U substitution, or you can just multiply the polynomial out and do it. So if you're interested in the procedure for completing this integral, you can just look in the textbook at the example. All of the work in this problem is in getting to the point where you actually have the integral. All of the modeling we did here about computing the volume, all of the stuff where we approximated the volume using ideas from calculus where we've chopped it up into the pieces, that's the sort of central philosophy of calculus, which is I can understand big problems as long as I can understand little problems. And if I can understand the little problem, then I can just add them all up, and that will give me a solution to the big one. Okay, so when you're done grinding all this out and you get numbers for it, I can actually check the text here. You end up with 3.4 times 10 to the 6 joules. Okay, so these problems can be a little challenging, the tank problems, but remember that all you're really doing here are these basic geometry problems where the same thing that we've been doing before is going to apply. We're going to look at a situation, we're going to try to calculate the volume of some arbitrary slice, and then we just have to know enough physics to convert the volume of that slice into, in this case, work that we can then integrate over to get an expression for the entire work done in a process. All right, I'll talk to you guys later.